Okay, so hi everyone. So yesterday we were discussing about the factors affecting the chassis frame design, right? Okay, so today we have to move along with the same topic and we will complete it. Then only we will move forward to the other topics as well. Okay, so factors affecting the chassis frame design that we were discussing yesterday. Factors frame design. Okay, so we found out like the things that are needed, they consider the forces that are acting on it, the movements that are acting on it. We have to be worried about the bending loads, the torsion that is going to be produced inside the chassis frame structure. We have considered this thing during braking or during acceleration or during hard cornering. Various forces and the imbalanced movements are going to be acted upon on our vehicle, which will lead to bending or will lead to torsion in the chassis frame structure. So while we were designing our chassis frame structure, we have to consider the geometrical aspects so that the bending, the deflection, the flex in the chassis frame structure should be as minimum as possible. Yesterday we have also discussed about the implications, the impact of the flex in the chassis frame structure, right? Like if you are applying the brake or the chassis frame flexes by a few seconds or something, right? Flexes like a quarter of an inch, a quarter of a millimeter, but it takes a fraction of a second. You can lose out a race, right? So geometrical implication as well as the physical implication we have, where we have to consider the material property, the selection of the material is very important, so that we could get to know about the strength of the material that we are using. Okay, so when we talk about the geometrical aspect, we have to calculate the area moment of inertia, mass moment of inertia and polar moment of inertia. Okay, we have already taken what is the effect, we have already considered what is the effect of moment of inertia in the chassis frame design, right? We have yesterday seen what is the effect of moment of inertia in the chassis frame design, which very much includes the forces. Now, what is the implication of area moment of inertia? And what do you basically mean by area moment of inertia? What do you even mean by area moment of inertia? So now, we all know what is inertia, we all know what is movement. For the moment of inertia, mass moment of inertia, we could directly say if anything wants to get into the angular motion, if any object wants to get into the angular motion, its mass to the distance of angle of rotation, this is the resistance that is going to be produced to give the initial angular acceleration, to provide the initial angular acceleration to the object, right? Now, when we talk about the area of moment, or what are we talking? Area moment of inertia. It's basically secondary moment of area or second moment of area. Now, second moment of area, it means there would be some first moment of area too. Mathematicians used to coin these terms. First moment of area. Now, in a basic mathematics, in a basic integral mathematics, you must have studied about the first moment of area. In your mechanics, your classic mechanics, you must have studied about the second moment of area. So when we talk about these terms, these are basically a geometrical interpretation of an object. Or better for your understanding, if I say I have got this pen, or if I have got any object, the bending load that is going to be applied on it, or the flex that is going to occur because of that bending load which I have applied, actually depends on the cross section of the area, or actually depends on the length and the dimension of the object under load. It does not only depend on the strength of material, but it also depends on the area of cross section under load. It means, like if I am having, just consider this thing, if I am having if we talk about a simply supported beam, two supports, and I have got a beam in here. I have got a beam in area. Just like in our chassis frame structure, this is the front part, this is the rear part. And I am talking about the static condition. I am talking about the static condition. Now here, if I am using a hollow shaft or a hollow material, you can directly say a hollow material, a rectangular material. Okay, a rectangular material. Let's not go with the circular. A hollow rectangular material, and the distance between these two is take it to be 70 inches. I was just randomly picked anyway, it has got no relevance. 70 inches. A hollow material with 70 inches. Cross section, or if I talk about the cross section, take it to be 1 inches, and this is, you already know, 70 inches. The thickness, take thickness to be 3 mm. Take thickness to be 3 mm. If I have applied in the mid, if I have applied at exactly the centroidal location, if I have applied a load of 100 kg, you can witness some of the deflection in here. Some of the deflection in here. Maybe this material is steel. Let's call it AISI 101. AISI 1018, having a very high value for yield strength or tensile strength. Okay, no problem. So I have witnessed a deflection in here. If I am going to replace this material with something else, take it SS310, take it SS310, or just leave this thing, take it EN19 or EN8 or AISI 4130 or some other very stiff or very strong material. Take any kind of material with the same dimensions, I can again witness the flex. That flex could be lesser, but again I will witness the flex in the material if I am going to apply the load. Now again, what else can I do? I have replaced the complete structure with the solid one. Now even I will replace it with the solid structure with the same dimension. Everything is same. Only the structure. Earlier I was using AISI 1018 hollow rectangular bar, but now I am going with a solid bar. What will happen? I can again witness the flex inside this. Flex inside it. Right? There would be a certain deformation whenever I will apply the load. Now we don't have the proper resources to show you these things in practical, but you can find these things, like if you have got a wooden bar inside your home or something, you can do these simple experiments at your place. Now just see this pen. If I talk about this pen, simply supported, right? If I will try to apply a load from here, you can see the deflection, right? I can't apply the load by holding it like this, right? But if I will apply the load in here, you can see the deflection. Now the second pen, its weight is absolutely same than of this pen. If I will try to apply the load, the flex in this pen would be lesser in comparison to the flex in this pen. Or I would say the flex in this marker would be lesser than the flex in this pen if the weight of both the pens are absolutely same, or the material of both the pens would be absolutely same, because here you can witness this pipe or this marker has got higher cross-sectional area, Now, so, or if I will replace it with the titanium bar, we don't have these resources available with us to show you these things in practical, but yes, definitely, many of the videos are available on internet, from where you can take the reference and can see how these things actually work. Take the reference means you can see the persons doing the practical over the same thing, right? Even if you don't have the resources, you can see or you can witness the other people doing the, other persons doing the, or showing you the practical implication of these theories. Okay, even if I take the titanium bar, I can witness the flex inside it. So it all depends on the geometry of the object or geometry of the subject that you have taken into consideration. The geometry of your design. This is very important. So when we talk about the area moment of inertia, which is also known as second moment of area. The first moment of area, when we talk about the first moment of area, which is completely a mathematical principle, it gives us the value of centroid. gives us the value of centroid. It means like if I take this square or a rectangle, if I take this square or if I take this rectangle, and someone asked me to find the location of the centroid. Location of the centroid. I told you everything in the vehicle is governed by the location of centroidal position. We already know in a triangle, the centroidal location is, if this is H, the centroidal location from this base, from the base would be H by 3. Would be H by 3. Now if I have to apply the load or something and someone asks me to calculate the second area, second moment of area. Now the second moment of area value will increase with the location of centroid. As the location of the centroidal location, as the location of the centroid rises up, your second moment of area will also increase. The first moment of area, that is, if I say at this point I have taken an infinitesimal small object or particle, take it like it's a distance from y, it's a distance from dy, having an area of dA or something, you can find out it's d centroidal location, basically denoted by S, like you can take anything. Okay, now if I take the second integral of this thing, the only difference between the first moment of area and the second moment of area is y dA. It's the distance of the location of infinitely small object from the base, right? This will provide us the second moment of area, which is a direct implication of the bending loads that are occurring in your vehicle, or which basically shows the deflection, which you can also call as the flex. This shows the flex. Higher the value of second moment of area, lesser is going to be the deflection. Similarly, for our vehicle, we have to increase the second moment of area. Yesterday we have discussed this thing. To have the higher value of moment of inertia, what do we have to do? Rather than having all the objects aligned towards the centroid, we have to move it far. If these objects are moved far, the pitching down of the vehicle could be reduced. Now when we talk about the braking and acceleration, it means the longer wheelbase. A longer wheelbase is required. And when we talk about the distribution of forces along right and left direction during cornering, it means we need the wider track width. To have the higher moment of inertia, longer wheelbase. To have the higher moment of inertia, to have the higher value of moment of inertia, the wheelbase and track width should have to be increased as much as possible. Okay, this will just talk about whenever we are going to apply the brakes, our vehicle should not tip down. But what about the bending loads in the static condition? Or what about the bending loads that are occurring in our vehicle while driving it? Maybe the weight of my driver will be shifted away from the center of axis, neutral axis. Then what will happen? At that time, we have to take into consideration our area moment of inertia. What our area moment of inertia? The area moment of inertia says. Now, see, if I am having this rectangular bar, consider this thing as a rectangular bar. If I am having this rectangular bar having a length of 10 inches, take it as an example, 10 inches, and this depth of 3 inches, 10 inches, 3 inches, simply supported, just like my vehicle, right? So I can say this is my chassis frame, supported by the tires. I have applied a load in here. We can witness the flex, right? Now, without changing any object, but just by changing the geometry. See, if I hold it like this and then I start to apply the load, the flex in the material will be very less. If with the same dimension I am going to use a carbon fiber, right, or on the other side if I am using the steel, the dimensions are absolutely same, but if I change the geometry, sorry, the weight is absolutely same. The weight is absolutely same. The weight of the material that we are using is absolutely same. But if I change the geometry, your bending, your flex, the visible flex would be very less. Right? So whenever we design a vehicle, we have to consider the area moment of inertia. Area moment of inertia, which So area moment of inertia, right? Area moment of inertia basically defines your stiffness. Basically defines your stiffness of the object, resistance to deformation, right? Or I could say to the strain, stiffness. So when we talk about the material selection, at that time we will be discussing about the strength of the material, while when we talk about the geometrical approach or geometrical interpretation, we have to consider the stiffness, or we will find out the stiffness, and stiffness depends on the geometry, and to find out the geometry we have to work on moment of inertia, area moment of inertia. Now in the area moment of inertia or second moment of area, there is one more thing that is known as polar moment of inertia. Polar moment of inertia, and polar moment of inertia plays a very crucial role, very crucial role. Now anything when is it in angular motion, we have to consider the moment of inertia. When any bending load is applied, we have to consider the area moment of inertia. But now when any twisting moment is applied, we have to consider the polar moment of inertia. For any object in this direction, in these visible direction, we can calculate the area moment of inertia, right? Along the length and along the width. We have just seen along the length and along the width, we have found the area moment of inertia. But what about the twisting force applied, the twisting torque applied along the neutral axis? See, this longest bar is the neutral axis. Right? What if the twisting force starts to apply at the neutral axis rather than having these parallel forces around the cross section? Now just remember this one thing, in the area moment of inertia, the forces are applied parallel to the area of cross section, right? Or I could say perpendicular to the neutral axis, Now in polar moment of inertia, when we talk about the polar moment of inertia, see, these forces will be acting, this torque will be acting along the neutral axis, Now polar moment of inertia and its relevance. We all know, if I am going to take two bars having the same weight and same length, having the same weight and same length, so its cross section will change. So if I am having two bars, a hollow bar and a solid bar, if I am having two tubes, a hollow tube, a hollow bar, hollow tube, and a solid bar or a solid tube, having the same weight and same length. Now if they are having the same weight and the same length, it means the cross section of both the tubes will change, cross section of both the bars will change. The hollow bar is always going to have higher value of polar moment of inertia in comparison to the solid bar. How? If I talk about the polar moment of inertia, so it's about, if I take a cylindrical bar, right, and if I start to apply the torque, or just consider this one thing, in your vehicle, this is the shaft. Along the shaft you have applied the torque at the edges. Now if in any of the condition, like jacking or in drifting, right? If in any of the condition the torque applied on one of the part is higher in comparison to the torque applied in the other portion, this will try to create the twisting in the shaft. This will try to create the twisting movement in the shaft. The twisting movement in the shaft. Now this will create the twist in the shaft, right? This twist is also known as twisting torque or the torsion produced. The torsion produced. Again, torsion. Torsion depends on the geometrical configuration of the object. Also depends on the geometrical configuration of the object. Now we all know, when we talk about the interim properties of the material, if any of the twisting force, if any of the twisting torque will be applied, the complete fiber, the material, the cells of this material will be changed, will be deformed, right? Their position will change. So if I take an infinitesimally small object inside it, if I consider any infinitesimally small object, I would consider the shape of this infinitesimal small object won't change, but its location will change. Yes, its location will change. Whenever I will apply any twisting torque, its location will change. And considering the location of this object having the area dA, we can calculate we can find out the torsion inside this rectangular or this cylindrical tube. Now shear stresses or the shear strain increases from the center of the neutral axis, to the upside edge, to the extreme edge, increases to the extreme edge. It means at the center, the minimum shear stress and the minimum shear strain can be witnessed. It means at the center, the minimum shear stress or the minimum shear strain can be witnessed, while at the edge the maximum is going to be C. Right? Show me pause करना. Okay, so now where were we? So we were discussing about the torsion in the shaft, or the polar moment of inertia, right? Okay, now as we see, there is a twist, or if I have got a shaft, just rub it down again, I will draw it. If I am having a shaft here, a rectangular shaft, having a length L, or in any of the condition, if the torque is applied, just give it this direction, the torque is applied, what will happen? It can witness a flex inside it, or the component here will change its direction. Earlier, the component, like this is a circular rod, there is a twist. I won't be able to draw it, like I'm not very good with the arts. So if I'm providing the torque here, I'm providing the torque in this solid cylindrical part, in this solid cylindrical shaft. What will happen? From here, this is the reference, I am providing the torque. You can see the flex is happening. The flex is occurring. So now the component, if I talk about an infinitesimally small component here, it will change its location somewhat to here, somewhere, like it will change its location, and it will change its location in an arc. Now this is the arc that is being created. Or I could say this will be created. See, the position of this part will change to this part. Now if this is theta is the angle of twist. I can calculate everything, like what is the exact value. Now for the infinitesimally small, or for the very small angle of twist, if I am having a very rigid bar, I am having a very stiff bar, this angle of twist will be very less, right? So now it would be, this distance will be r theta, and this would be L. Now for the very small angle of twist, visibly, like it's not possible to visibly see the angle of twist in the bars normally. So we can consider, we can say that the angle of twist is very small. This would be tangent of theta would be equal to theta in the cases when the angle of twist is very low. Or even if we are going to consider the cases where the angle of twist is very high, we can directly take it tan theta. Tan theta is equals to, sorry, we won't take it tan theta, we will only consider theta at that time when the angle of twist value is very high. R theta by L, right? R theta by L. This is what we chal raha hai. Okay, now this is something that we can consider. Now this value is very less, and for an infinitesimally small object, and the infinitesimally small angle, if I take this thing, infinitesimally small angle and the infinitesimally small distance, radius, like it could be anything, like it could be here, it could be here. This is R, not this, right? So this will be rho theta. This will be rho theta for this angle which is very small. This angle which is very small, I can say this is R, or better I would say rho theta by n. This is rho theta by n, or this is the shear strain produced. This is the shear strain produced. Or when we talk about the polar moment of inertia and its implication, again polar moment of inertia is the torque applied or the moment applied across the neutral axis, along the neutral axis. So it would be again double integral of ये. It would be exactly same what we have got in the second moment of area, right? Or area moment of inertia. The formula would be exactly same, but the only change is here we are applying the moment along the neutral fiber, along the neutral axis, while in those cases we were applying the loads or force parallel to the cross section area or perpendicular to the neutral axis. Here we are applying the torque, there we are applying the forces. The implication, the formula is absolutely same, but their implication would be completely different. Now, in this case, I can see if I have to find the centroidal location, the center of location of my infinitesimally small object, if we can consider any place in this rectangle, cylindrical bar or the cylindrical shaft, we can see this R, or I can take it as an X. X is the distance of this object from the center fiber. Or if I have to calculate the polar moment of inertia, it would be x square dA. Now in the complete rotation, you can find out what is going to be its relevance. I have applied the torque T here. Which will produce the shear stresses tau inside it. Inside it. Now this tau or this torque, if there is an imbalance between the T and tau, what will happen? This T by tau will create the shear strain. This T by tau, because of this T by tau, we have got the angle of twist. I am not saying this. Because of this, we are getting the angle of twist. The shear stresses that are being generated, the imbalanced shear stresses that are being generated because of the imbalanced torque. At this position, I have got the higher value of torque. At this position, I have got the lesser value of torque, or maybe the zero value of torque. This torque will create the tau, the shear stresses inside it, and this shear stress will lead to angle of twist, which has got a relation T by tau is equals to J by shear strain. This J is the polar moment of inertia. Now for the second moment of inertia, we used to say I. For the polar moment of inertia, we denote it by J. and this is the shear strain, and this term T by tau torque applied by the shear strain produced is known as section modulus of a shaft. Even for a beam we have to calculate the section modulus. Even for the beam we have to calculate the section modulus. But at that time, this J will be replaced by I. This J will be replaced by I, and the equation goes like this: M by I. In the case of beam, the equation will change upon sigma by Y. M by I equals to sigma by normal stresses, normal strain, and this is the location of the point under scrutiny, is equals to E by R. Now, while designing the chassis frame structure, again I will repeat it. First, we have to calculate the moment of inertia, mass moment of inertia, then area moment of inertia, which has got a very high relevance with the bending and with the performance, or I could say better, for this thing we can take it for the flex or for the tipping of the vehicle. Tipping of vehicle, not the flex, tipping of the vehicle. Here I can say the flex inside the vehicle, the flex inside the vehicle, not tipping of the vehicle and flex inside the vehicle. In this case, your vehicle tips off, complete vehicle tips off, and in this case, your vehicle bends down. Third is the polar moment of inertia. Now, in case when our vehicle is taking a very high speed turn, we can directly change it with the area moment of inertia too, because both have got the same implication if we talk about the beam. And if we talk about the shaft, polar moment of inertia is very important by deciding it. Now, I told you the shear stresses increases from the center. The shear stresses increases from center, from the neutral axis to the extreme fiber. The value of the shear stresses start to increase. So you can find out, like if you go with the analysis on any of the software, you can find out in this region, inside region, or in the near vicinity of the neutral axis, it opposes very less to any deformation or to any twist. The opposition or the resistance to deformation or twist by the material inside this area or near to the neutral fiber is very less. And even you know T by tau equals to J by R. Right? It means we have to increase the J. We have to increase J as much as possible to have the very less value of angle of twist. To have the very high value of angle of twist. Or I can change it like this: tau, shear stress is generated, equals to T into R by J. If we would be able to increase this J, the shear stresses produced will be reduced. And how to increase J? If I am having, just take an example, I am having 5 kg of shaft. See, in this diagram, we haven't considered any of this thing. We haven't considered the strength of the material. We have just considered the geometrical implication of the material. The strength is also important. We have to consider the Young modulus too, right? Or the shear modulus. We have to consider the shear modulus, but that comes on a later part. Now, if I am having a 5 kg of shaft, 1 inch solid, AISI 4130, or just leave it 1 inch solid. I am just taking the examples, right? AISI 1018, 1 inch shaft solid, 40 inches length. Now again, AISI 1018. It's not recommended to go for AISI 1018 if you are going with the shaft. Take it 1.5 inches with 4 mm thickness. I haven't calculated these things. You can take any of the examples, and 40 inches of length. There are chances, I'm still not sure, but yes, if we go with the proper calculations, you can find out. The stiffness or the polar moment of inertia of AISI 1018 with this configuration 1, configuration 2. The configuration 1, the stiffness of configuration 1 will be very high in comparison to the stiffness of the configuration 2. The stiffness of the configuration 1 is very high in comparison to the stiffness of the configuration 2. Now there is one more thing. If we have to calculate the angle of twist or the shear stresses produced inside any of the object, for the ductile material, if we are using any ductile material, the deformation occurs because of the shear plane, maximum plane of shear stresses. The deformation occurs because of the plane of maximum shear stresses. And for a brittle material, the deformation occurs at the plane of maximum normal stresses. For a ductile material, deformation occurs at the shear plane. For the brittle material, deformation occurs at the normal plane. Right? For that, you can draw the Mohr cycle diagram. You will get a better understanding about the same. Okay. Right? So you got this thing. Now, polar moment of inertia is very important. For the complete vehicle, polar moment of inertia should have to be calculated, which will counter the torsion in your vehicle. Yes, the torsion in your vehicle. During high speed cornering, there are very high chances of torsion. In a vehicle.